So welcome to the statistical methods section. We will be starting off today with Adam Watts, who specializes in applying statistical methods and uncertainty quantification to complex engineering challenges. His research interests focus on functional data analysis and computational statistics, with an emphasis on leveraging these methods to solve engineering problems. Adam is an R&D engineer on the data analysis team for test engineering at Los Alamos National Laboratory. He holds a bachelor's in Plastics and Composites Engineering from Western Washington University and a master's in Textile Engineering from North Carolina State University. And he will be talking about, and I'm not even going to try the whole title, but functional analysis of variance tutorial. So take it away, Adam.
Hi, good morning, everyone. I'm super excited to be speaking here. So this is a functional analysis of variance tutorial. Things like when I started doing functional analysis of variance, what did I want to know as a practitioner, and what are the things that I've gleaned over the years of using it, and things that I've learned along the way from even writing libraries for this. So the whole underlying theme is kind of grouping data and identifying interactions across arbitrary domains. So before going to functional analysis of variance, it's probably a good idea just to get a refresher on classical ANOVA or classical analysis of variance and some stochastic processes. So classical ANOVA is used to test whether there are significant differences between the means of scalar random variables measured across multiple groups or factors. Compares the variability between the groups, to the variability within the groups. Unfortunately, many natural processes are not scalar random variables. Some of them may consist of a collection of random variables known as stochastic processes, denoted as SP. And it's generally over some type of domain of interest, and denoted as capital script T here. It doesn't have to be time. I often work in frequency domains, so autospectral densities, could be shock response, mechanical shock and vibration. But for the most applications, time's easy to kind of wrap our heads around. Some examples include temperature measurements over time. So the plot shown here, they have two groups, some type of temperature over time. We would like to know over some domain, is group 1's mean different than group 2's mean? Can also be, like I said, shock response over frequencies or other type of measurements over some type of domain. So functional analysis of variance, I like to view it as basically if you had a ANOVA family tree, how we break this down. So classical ANOVA is what most of us have learned in our statistics courses, and that's over scalar random variables. And then further down, you're basically asking, is there equality of, k means, mu1 equals dot dot to mu sub k. Functional analysis of variance is over stochastic processes, so it's kind of extension of these mu's, but it's mu as a function. So mu1 as a function of time 1 all the way through mu as a function of time to sub k like factors. So functional ANOVA works on stochastic processes. This is a global test compared to a point-wise test. So if we had to do classical ANOVA over a function, we may want to say, hey, I want to slice it over time. And then if you had 1,000 time points, like what do I do with 1,000 tests? Functional ANOVA is nice because it gives you a global-wise p-value over that entire domain. Like I said earlier, for convenience, we can assume the domain is over time. So t is an element of our time domain. So it's easy to think about and going forward. So functional analysis of variance is used for testing whether there are significant differences among the mean functions of stochastic processes over some domain measured across multiple groups. It's kind of extension of classical ANOVA. So something to kind of think about is F-ANOVA in practice versus theory. So F-ANOVA is based on functions, but all samples we collect are vectors. We collect discretized data, some sort of a data acquisition system. So numerical implementations of F-ANOVA are based on these vectors. So for the ice functional sample are discretized accordingly. So we say y sub I is independent and identically distributed through some stochastic process with some mean function mu and some covariance function gamma. We discretize this, so I have a capital Y sub I, and these are just at some time points t1 through t sub capital M, and these are discretization of our functional process. So in practice, the mean function mu sub 1 of t is really a capital mu vector, so we have a mean vector, and our covariance function is actually in practice a covariance matrix, which I denoted as capital sigma. So data pre-processing for ANOVA. So what do things like do I need to know about to actually utilize functional analysis of variance? One, data has to be sampled over a common domain. It doesn't have to be uniformly sampled. It can be non-uniformly sampled, but just has to be consistent among all the realizations. We can't have one realization at time equals 1 and the second realization at 1.2. They're not, happening over the same moment in time. It can be a stationary or non-stationary stochastic process, so either one. Um, Another thing is a resolution of each sample sufficiently long, or how many data points do we have per realization. Generally, the best practice is to have 1,000 discretized elements per realization. It's actually quite a challenging topic to say how much is enough. It really depends on your data, how much noise, what is the variance of the covariant structure of the data, how are you, what signal processing techniques are you doing. So it's actually, I played around with this for actually a day or two and realized that it's not as intuitive as you would think. But generally, the best practice is 1,000 elements per realization. If you have less than that, um, like so for example, the data doesn't meet these requirements, you can functionalize it using some type of B-splines, P-splines, or other type of kernel smoothing methods. So let's start with a trivial example. Suppose we collect room temperature data from 3 different rooms over the course of 25 hours. And we collect 15 samples from each room. We have rooms A, B, and C, and 1 through 15, we've collected 15 independent samples from each room. So we have one factor, which is our rooms, A through C, and then we have 3 different levels or groups within those rooms, like I said, A, B, and C. So we're going to, just for this example, have each group has a different covariance function, and the data sample uniformly, but more importantly, consistent across the domain. So here we have time going from 0 to 25 hours, and each realization has 3,000 elements within our hours. So the question we really want to ask is, does the mean temperature statistically differ across the rooms? And if so, which ones? And how do we actually do this? So here's some example data plotted. We have room A, which is this blue. We can see there's some highly cyclical behavior. Maybe someone has a space heater that keeps cycling on and off, on and off. They can't get the right temperature in the room. Room B is, really cyclical or really, really noisy. Maybe there's a lot of, a door that opens and closes consistently, people walking in and out. And then we have room C, which has basically big shifts, but less shifts within the hours. So we really like to know, is the mean function of A, B, and C the same? If so, which ones are, and is it over the entire domain? So it gives us an idea, kind of what the question we're trying to ask and answer going forward. So someone who's using functional analysis variance, there are libraries. There's one in R that is called F-ANOVA. I wrote one in MATLAB, which is similar, but has some other features which I'll explain more. But if you use any of these libraries, like something would be like nice to know would be like, actually, how does it work? So this comes back to the central limit theorem of IID stochastic processes. So the test statistics throughout functional analysis variance are distributed as zero mean Gaussian processes, which I've just denoted as GP0, gamma. So even when the Gaussian assumption of D is not satisfied, the difference between the sample mean and the actual mean function converges in distribution to a zero mean GP when n is large, or sample size is large. And so that's how I've denoted here. Try not to keep too much statistical notation, because just trying to give you the things you need the most to actually apply this as a practitioner. There's phenomenal books on this that go deep into the derivations if you're interested, which I've listed here as well. So from this, it can be shown that the difference between group means functions converges in distribution to a zero mean Gaussian process under the null hypothesis. So ultimately, it may converge to a zero mean Gaussian process, but why do we care? Well, why is this useful for us? Well, the squared L2 norm of a zero mean Gaussian process is actually a chi-squared type mixture with degree of freedom k. Denoted this here with the square notation as a L2 norm. Lambda here is our eigenvalues from our covariance matrix, and y is a sample from a GP, or distributed as a GP process. And A here is IID chi-square random variables. So all the F-ANOVA methods are based around this chi-square type mixture distribution, because it serves as our null distribution. And when you run a F-ANOVA test, ultimately you'll get this type of null distribution, and then we want to know, how do we actually utilize that null distribution? So there are approximations using naive or biased reduced cumulative matching for this, and there's also direct simulations for how do we actually calculate this null distribution, this chi-square type mixture. And so, like most tests, we compute a test statistic from the data, compare it to its null distribution to see how probable that statistic is under the null hypothesis. So that's kind of a 2-slide summary of actually how does F-ANOVA actually work. So here's a nice kind of diagram. So when you run these tests, whether it's an R or in MATLAB, you'll have lots of different tests, and really they come down to two families. You have an L2 type, which we described, and F type, which I'll describe more in detail. So L2 type has its own kind of little family tree. The stuff in the dash boxes, those are just uh, ways to simulate that null distribution. And then the solid yellows are basically more numerical ways. So let's go into the L2 norm type. So F-ANOVA for the L2 norm type test. So when would I use this, or what are the kind of assumptions? One, it's either the data comes from a Gaussian process or you just have large sample sizes. So in this case, the null distribution is chi-square type mixture, and there are naive or biased reduced approximations methods to calculate this null distribution or estimate it. Another option is you can simply Monte Carlo simulation of the null distribution. So we have those eigenvalues from our covariance matrix, and we can just simulate tons of chi-square type random variables, and then we can estimate this null distribution with large Monte Carlo simulation. In the cases when the data is not Gaussian from a Gaussian process, or you just have small sample sizes, which is most of the time Los Alamos have small sample sizes because it's expensive to fly the F-35 around or some other aircraft. We can bootstrap the critical values, resulting in L2 norm type bootstrap test. That's denoted kind of over here on the far right, bootstrap, non-parametric bootstrapping. So bootstrap the data non-parametrically, calculate the bootstrap statistics from each bootstrap resample, and then we can estimate the 100 comma or 101 minus alpha percentile, the test statistic for the given data. On the other side, we have the F-type distribution. So really the F-type is just a specific type of the L2, which I'll explain. So here, F-type is you need to have a Gaussian assumption, and this to do so, we partially take account of the variation of the covariance matrix. And we can think of the F-type as just as a very special type of L2 norm type test. It's really just a normalization factor using the trace of the estimated covariance matrix. So if you simply don't have the trace of the covariance matrix, you have an L2 norm type test. Nice benefits of the F-type test is the scale invariant. You can multiply the data by a non-zero constant, and it doesn't change the test statistic at all. And it is expected to outperform the L2 norm type test, particularly with that, assuming that Gaussian assumption. And the null distribution is actually an F-type mixture, so it's just a ratio of two chi-square type mixtures. And once again, we can either approximate this using, like I said, naive or bias reduced cumulative matching methods, or you can simply Monte Carlo simulate that null distribution. For the F-type, when the data is simply not Gaussian, regardless of if you have a large sample size or not, you'll have to bootstrap it, resulting in an F-type bootstrap test, similar to how I described the L2 one. So what test should I use? As a practitioner, I really like non-parametric L2 norm and F-type bootstrap tests. They're robust, they require the least number of assumptions, such as being Gaussian. However, there is a caveat, which I want to say, is which they can still struggle with very low sample sizes. So when you only have functional data of sample size less than, say, roughly 7, you really are limited. And I want to show that on the far right. So here's n, and on the next column over, you have unique bootstrap samples. So when you have less than 7, you may be able to bootstrap it. In fact, you can actually describe numerically how many unique bootstrap samples you can actually get. So while these are great numerical methods, you can get something from nothing. So if you have 3 or 4 samples, you're very limited of actually how do you actually build that null distribution. So with really low sample sizes, you're limited. You just, like I said, you can't get something from nothing. The cumulative matching and direct MC simulation methods are fast. They're computed in less than a second, so it doesn't hurt to include them. And I mostly include them mostly because it allows me to see what assumptions hold and which ones do not. So if I see that the naive method and the Monte Carlo ones are very similar p-values, that means that the naive approximation is pretty good to actually my null distribution. So variance of F-ANOVA. So there's a lot of, just like standard analysis variance, there are some assumptions. One of them is heteroscedasticity. So that means, at least for the heteroscedastic F-ANOVA, the variance doesn't pull the covariances. So traditional analysis of variance, unless you specify, you assume homoscedastic. Basically, they share the same covariance or same variance. Functional analysis of variance can actually can be modified to support heteroscedastic data. So even if someone may come to me and say, "Hey, my data, shows heteroscedicity," I can't use it. And I also say, "Well, you can use it. You just have to use the right test." There are some modifications to L2 and F-type tests that take this in account. Um, One thing I would recommend is to check the equality of covariance to pick which F-ANOVA variant to use, or you can simply run both heteroscedastic and homoscedastic methods to see, whether those two p-values match, or if they do, then great, you probably do have homoscedastic data. If they don't, then probably should choose a heteroscedastic variation. So like I said, if it's homoscedastic, then great. Both the variants will provide similar p-values. Um, in the case that it is homoscedastic data, the F-ANOVA for the homoscedastic will have slightly greater statistical power because you are pooling those covariance matrices. So if you have 5 groups and they all share the same covariance matrices, then great. You're pulling from 5 groups. You have a lot bigger sample sizes to estimate that covariance function. So here's our example data again. So we want to ask ourselves, which groups have same mean temperature over this time domain. It looks like just eyeballing that A is different than B and C, but it's hard to say because from 15 to 25 hours, it looks like they come and match up again. So kind of here's the ideal workflow. So for data preprocessing, if you need to, it has to be sampled over a common domain. Ideally, you have roughly 1,000 elements per sample. You can plot the data to visualize this. Pick some statistical significance. Here I've chose alpha as 0.05, so very traditional. Check the assumptions. Is it data heteroscedastic? Is it homoscedastic? You can visually check this by which I'll show shortly. Or there's also statistical tests for the equality covariances. Run the appropriate F-ANOVA variations, and then any post hoc test. So if F-ANOVA does say that there is a difference, just like standard analysis variance, we need to know which one it is. It just states that one of the groups, one of the levels within our factors is different, but we need to know which one it is. So checking our assumptions, here's a plot of the covariance matrices. So room A, which we said someone had maybe a space heater going, cyclically on and off. You can definitely see that in the covariance matrix. B, very tight along the diagonal, and C is more diffuse along the diagonal. And if we pooled it together, which would be if we use the homoscedastic variation, this is what the covariance matrix it would be pulling from. Running an equality covariance test, which also happens to be you can see the math behind it, but it also happens to be the null hypothesis happens to follow a chi-squared chi-squared mixture distribution. We can calculate p-values, and we find that they're statistically different. And we can visually see that, yeah, these covariances are statistically different. If we went back to plots, just visually we can see, yeah, room A has very different covariance structures than all the other ones, particularly even B and C. So, and when I wrote this synthetic simulation or data, I wrote it such all 3 had different covariances. So this matches what we assume, and visually it matches what holds up. So running the F-ANOVA, the heteroscedastic test, here this is what pretty much every library will provide you. So if you use an R, or if you use it in one I wrote in MATLAB, you'll get a big table like this. And so for as a practitioner, it's a little bit overwhelming. Before in standard analysis variance, we just have one p-value. Great, move on. Here's like a whole table, and it's like, well, which one do I use? And the reality is, like I said, it depends on what the data assumption is. But here, among the L2 and the F-type, all the p-values are incredibly small. And then when I ran this also with the homoscedastic assumption, p-values were slightly different, but also pretty small as well. So it's very little difference between, at least for this particular data set. So we would conclude that the means are statistically different because the p-values are much smaller than we've said or stated at 0.05. But then we need to do a post hoc test. So here we've done a pairwise heteroscedastic F-ANOVA pairwise test. So we want to know which rooms are statistically different from each other. And if we went back a couple of slides, we'd think B and C probably are the same, but it looks like A is different than the rest. And if we come over here, we can say when we run these F-ANOVA tests, room A versus room B, no matter which F-ANOVA test you've used, and also which assumption it was, whether you naively estimated that null distribution, we find that p-values are all much less than our critical value. Same with A and B and A and C, and not surprisingly, B and C, the p-values are at 0.5, actually quite high. So So we can state that room A statistically differs compared to room B and C, but however, we fail to do so for room B and C. So this allows us to actually dive into our functional data over this domain and see which means are different. So another question is, a nice thing about functional data is like, what if we subset the data? So when I wrote this, we have 3,000 data points. Subsetting this, we still have a lot of discretization of points. So between 50 and 25, that's kind of where we thought, hey, so it looks like A actually comes back to meet the temperature of the other rooms. And we can run a similar test on this. So for running the heteroscedastic, we can see over at least this domain of our time that we don't have enough evidence to state that the room mean temperatures are statistically different from each other. And this kind of goes with our kind of rough eyeball check. But the benefit of functional analysis of variances um, doesn't you previously when I've talked to other people, at least in my domain of applying this for mechanical shock and vibration, a lot of times it goes back to subject matter experts. Someone would say, this looks roughly the same mean, this looks roughly the same. And to me, that always bothered me because it was analyst dependent. You give it to some other analyst, they may say, well, this looks slightly different when it isn't. So the benefit of functional analysis of variance, it gives you a quantitative value of, is this different or not? So variance of F-ANOVA, there's also, we talked about homoscedastic and heteroscedastic. There's also two-way analysis of variance so just like standard analysis of variance. So you can do one way, which we've been shown. There's also two way. So one way, just to clarify, that's whether the mean functional response differs across multiple levels or groups. So in this case, it was like we could have temperature as our factor. We could have 3 different levels, 30, 60, 100 degrees Fahrenheit. Pretty simple example. It's a two-way one. It's whether the mean functional response differs jointly across two factors. And you can also test for interactions between these factors. Just like standard ANOVA, functional analysis variance can also support this. So perhaps we had temperature and humidity as our two factors. Each of those have their different levels. So temperature, same 30, 60, 100. Humidity may just have two levels, 10% and 90% humidity. And you may want to know interactions. For example, if I ran a test at 100 degrees Fahrenheit with 10% humidity, is there an interaction between these two variables? And lastly, I want to just discuss differences between existing F-ANOVA libraries. When I came across this, the only library that existed was an R. I have no problem using R. I do statistics a lot, but trying to convince other engineers to do mechanical shock and vibration to take their data and put it in R, do some statistics, take it back out, and put it back in MATLAB, it's an uphill battle, put it that way. So instead of trying to force everyone to use R, I said, well, most of our analysis software is written in MATLAB. Why don't I just write my own library? So that's basically what I did. So here's some links you can click on. Both these are open source. The LANL's F-ANOVA is on a GitHub Git page, LANL's GitHub. It does similar F-ANOVA methods. The only thing, there's some similar differences on a few features. For example, I wrote the Monte Carlo simulation, so you actually calculate the null distribution. The R method doesn't do that, but there's also some basis function representations. Data types, the R method does support multivariate functional data, which is great. When I wrote mine for MATLAB, it's just univariate. Some of the bigger differences, particularly, is heteroscedastic support. The R method just has one, which is the L2 norm parametric bootstrap. The one in MATLAB that I wrote supports all methods. So you can, L2, F-type, all the naive, every other method supports that. And design, since I do a lot of test design, it supports two ways. The standard one in R just supports one-way analyses. So we can do a little bit more additional analysis in MATLAB version. And also post-hoc test. R just says something's different, but which one it is, well, you run more tests. You'll have to do that. And the one I wrote in MATLAB, you can easily do a pairwise hypothesis. You just state on, it's an object-oriented approach to it. You can simply state, I have my hypothesis is pairwise. I'll run all the pairwise tests, every single combination of pairwise tests. And lastly, the MATLAB one does provide some visual and statistical tests for covariance testing. So key takeaways. F-ANOVA works over a variety of scientific fields. If your data can be sampled over a common domain, you can utilize F-ANOVA methods. Provide sufficient resolution for each sample, so roughly 1,000 elements per sample is a good takeaway if you want to do no signal processing on your data. But even still, you may have to, if you use less than that, you may want to increment upwards. So start with 500, check the p-values, go up to 800, 900, make sure that you actually hit convergence of the test statistic. And lastly, F-ANOVA can support heteroscedastic and homoscedastic data to pick the right one. It can support data that does not originate from a Gaussian process, which is really powerful. A lot of data that I get from mechanical shock is not. Can support one and two-way analyses and can support low sample sizes because bootstrap options exist up to a point. Thank you.
All right, we've got some time for questions. I don't see any online yet, but anybody in the room have one? I was gonna say there's no microphone over there for you, so.
Yeah, thanks for your talk. I'm wondering, I noticed a lot of like periodic oscillation in your data. I'm wondering if you have techniques that like, I guess, accommodate something like a Fourier analysis or trying to characterize the periodicity of your data.
When you say the periodicity of your data, are you looking for can I utilize that in the functional analysis of variance, or what aspect of that, I guess?
Yeah, so like, right, room A.
Sure. When I did room A, I actually did that kernel is actually a sinusoidal periodicity. So that's why you see that. And same with the covariance plot here, you can see that periodicity. I
Right.
don't know why I did.
Right, because like if you're just comparing the means, maybe they are the same, but obviously A is the variations all over the place.
Sure,
In
correct.
comparison to like, if you did a did a Fourier transform and then ran your statistics, you would find really different results.
So the Fourier transform would, at least from my knowledge, would only work for a stationary process. So here, this process is not stationary. We have a mean that's shifting over time. So you'd have to maybe do a short-term Fourier transform over that. So it becomes a little bit more challenging of how to do any type of signal processing for non-stationary processes. At least in keeping it in this domain, not doing that transform allows you to do those statistics. Hopefully that answers your question. Ish. Okay.
Any other questions?
Hello. Thanks for the great talk. It's really, really interesting. I was curious, on slide 9, you talk about this mixture of chi-squareds, and I've seen this in one other place before, which is if you're doing hypothesis testing with a composite null, and let's say you're just testing if your parameters in like the non-negative orthant versus not, and it turns out that the likelihood ratio also under the null has a mixture of chi-squareds, and they call it the chi-bar square distribution in that literature. I'm curious if there's a connection here, and if you can look at these, the test statistic here as in some way, some sort of constrained context. Thank you.
I'm not sure your particular domain on that topic. I do know at least how it comes about is at least the chi-square comes from really the covariance matrix, and so you're basically summing along the diagonal, at least of those eigenvalues. So how I envision this is really the decomposition of the covariance matrix, and because it's a summation along all the eigenvalues, positive eigenvalues, that's how the chi-square mixture comes about, and you're scaling it by the eigenvalues because how it becomes a chi-square is because of that. Can go back real quick. The central limit process. Like if we didn't have this central limit process, we wouldn't have convergence to a chi-square because it's like a standard chi-square is just a sum of a squared normal random variable. So if we didn't have that, then we couldn't get that convergence or get that particular chi-squared mixture. So that's why when we have a non-Gaussian process with low sample sizes, we can't actually assume that, and so that null distribution is untractable, and so we just have to basically parametrically bootstrap what that null distribution is. I'm not sure if that.
That's definitely helpful. I also noticed that so in the chi-bar square distribution, the degree of freedom of the chi-square distribution is indexed with the
Correct.
sum, whereas here it's k for all of them. So I guess that is a bit different. But anyway, I don't know. I guess that's not what I was thinking. But
The k can change a little bit, particularly when you talk about like the heteroscedastic because each group has its own covariance matrix, and each of those covariance matrices may have different sample sizes. So group 1 may have 15 samples, so you have 15 degrees of freedom minus 1, so 14. And then the subsequent one, you may have a group, maybe B only had 10 samples, so therefore you'd have 10 minus 1, 9. So I wrote this as a really simple, very, very basic, just again, general overview. But yeah, that degree of freedom can change whether you're pooling the covariances or you're treating them as differently. But yeah, they're based on basically your sample size.
All right, let's thank our speaker one more time.